Okay, ready to go? So just a quick recap. So we're talking today about the system boot, right? So our goal today is to boot into main. So essentially, if you, in the end, your kernel, you can think of it as a regular program, right? And it doesn't have to have a main function like with a specific main name, right? But it's just the convenience, right? So, and your goal is to boot to that main, right? Our goal today. The real question is, what do you think we need to do to achieve this goal, right? So, in our like, well, we'll do it step by step, right? So last time we said, okay, like a lot of things are running before even the bootloader starts, right? Because there is this Intel management engine, there is system BIOS loads system management mode. Those things is running all the time on your machine. But the way it ends is that BIOS loads a bootloader from the first sector on disk, loads it in memory at the address 7C00, right? So it's just 512 bytes. So it's a tiny bootloader, right? And we have it, so we control it. So we don't control BIOS, so someone else wrote BIOS for us, right? So someone who was working on the software essentially, and like on your personal computer, essentially, like a manufacturer who typically contracts with the developer of BIOS and customizes it in some way to boot a specific piece of hardware, right? But anyway, so at some point we said, okay, we're gonna jump to BIOS jumps to 7C00. We briefly discuss how we will compile a bootloader which runs there, and essentially our system looks like this, right? So this is a tiny boot block which BIOS loaded into just the size of 512 bytes, and it's loaded at 7C00, right? Remember, the way x86 machines were starting in the past, they were starting in 16-bit mode, right? So essentially, even if the BIOS switched on 32-bit mode, used like page tables and stuff, everything is turned off. So at this point, we're starting at 16-bit mode, no segmentation, no paging, right? And if I ask you to tell me what will be the outline for how to boot into main, try to guess a couple of things. What do we have to do?
Bring the kernel to memory and start running memory.
Okay, bring kernel to memory from disk.
Yeah.
Okay, yeah, that's a good thing. Then you say start running what?
The kernel in the memory.
Jump to the entry point. Let's say it's main, right? In order to run main, which is C, right? What do we need? What kind of execution environment we need to start running main? It's kind of like a runtime for C in general. Your main will look something like main will start like init something, I don't know, init some functions here, right? For C to run, what do we need? C is a very friendly, OS-friendly language because it was developed to specifically build low-level code and stuff like operating system kernels, right? And it was developed by the people who were building the kernel. So C doesn't run without a stack. So the runtime for C is very, very minimal, right? So there is nothing. But if you wanna compile this code, right, assembly will compile it to something like call init, right? And for this instruction to succeed, you need stack. Agree? So then we need to set up stack, right? So what else? What else do we think we need to do?
Well, jumping to the entry point, like easy enough for it to make. Like we know exactly where it is for file.
Right. So since when we bring kernel to memory, so kernel is will be compiled as an ELF binary, right? So we can look up the ELF header and see where the entry point is. There is a little bit of a trick here, right? Because you say, look, we can choose where the kernel will be running at address 0, at address first megabyte, at address whatever, right? So we will compile the kernel and link the kernel in such a manner that it will run at a specific address, right? We'll see in a second. But that's right. So, but what else? Like, what do you think else? What else needs to be done? We started on it. First of all, like remember, we started in 16-bit mode. Like all the registers are 16 bits. Like EAX doesn't exist because EAX is the 32-bit register. Only AX exists, right? That's a little bit awkward because we clearly have a 32-bit machine, so we need to switch to 32-bit mode, right? Right? In order to switch to a 32-bit mode, we have to enable segmentation. And as I will explain later, segmentation controls privilege levels, meaning you probably heard it like rings, ring 0, ring 1, ring 2, ring 3, right? Ring 0 is the most privileged ring. So kernel runs in ring 0. It can access all the hardware instructions because some instructions are privileged. And if you try to invoke them from ring 3, you'll get an exception. That's to ensure that user level code cannot abuse the kernel, right? So we'll set up this privilege rings as well. But obviously, since we are so smart and we know that segmentation is not ideal for modern world, we will try to set up a page table as well, right? Because we say, look, the kernel will be managing physical memory, right? So when we boot, entire memory is available. And as we start like loading the kernel, initializing the kernel, starting the first process, we will have to keep track of which physical pages are available and which are not available, right? So we'll essentially like set up paging as well, right? Okay, so and that's more or less what we have to do, right? So essentially, we will do a couple of things. We will set up segmentation inside the bootloader. We will load the kernel to memory, obviously from the bootloader as well. And this bootloader is this 512 bytes, which we provided, like wrote into the 0 sector of the disk, right? So, and the BIOS just followed the protocol and loaded it at the 7C00, right? But essentially, we will, like, this bootloader will talk to the disk and load the kernel in memory. And then the kernel will enable first page tables and will create a first address space in which the kernel will start running, right? So, okay, that's the outline. So let's, again, start working on it, right? So that's essentially, this is the same sequence, but just, it has a little bit of details which will become clear as we go forward. Okay, we were looking at this code last time, so it's the same. So this is the very first line of your boot block, right? So remember, there's 512 bytes, right? So we say we will disable the interrupts because maybe BIOS was talking to disks and networks, maybe interrupts were enabled, and BIOS probably set up an interrupt descriptor table to handle interrupts, right? And I will explain how we handle interrupts in general, but in a couple of weeks, right? But we say, okay, since we probably may overwrite the interrupt descriptor table accidentally in the next step, let's disable the interrupts because it's just safer this way, right? And then you say, look, since I'm about to enable segmentation, we will zero out the EAX register and essentially put 0 in the DS, ES, and SS segments, right? Just again, because we're still running in 16-bit mode, segmentation is not enabled, but the moment we enable segmentation, remember, the CPU will implicitly use the values of the segments, right? import of every instruction, right? So move will use a data segment, push probably uses stack segment or data, I don't even remember. Code instructions like jumps will use CS segment, right? So we'll just be safe and just make sure that those segments are zeroed out. Maybe bias was using something else as well. And I was explaining that in order to compile or to link the boot block correctly, we'll explicitly say that, okay, we will run at 7C00, right? Just because there is no position independent code, although it's possible to probably compile it with the, no, it's not really possible. You can tell me, why can't we use position independent code here at this level? At the level of bias in the kernel? I mean, we technically can, but an additional convention is required here. What is this convention?
Are we worried about accessing system calls?
There are no system calls yet, right? Because system calls typically lead you from user level to a kernel. You'll be an expert in system calls in a couple of weeks, I guarantee. No, remember, position independent code requires global offset table, right? And if you, right now, you have to then require bias to essentially set it up for you, right? And that was not a convention. The bias just blindly loads this 512 bytes from disk, boom, and just doesn't do anything, right? So if you say that I expect that my GOT is in some correct state, someone has to do it, right, for you. Typically, the operating system exact code will do it for you, right, the kernel, but we don't have it right now, right? So because machine is just bare thing, right? Bias can be as capable as operating system, but okay, like in modern biases are, but the convention is that it will just, like, legacy convention is that it will just load this 512 bytes. That's why everything is linked statically. And if you have a global variable, which you refer to in one of those C files like boot main, which you're using here, then you will be screwed unless you say, okay, please link everything to run at 7C00, right? Is that clear? Okay. So, and the first thing we want to do, like, bring back the 32-bit mode of execution, because 16-bit mode of execution can only access whatever, 2 to the power 16, which is what, 64 kilobytes of physical memory, right? So it's clearly not enough. So we say, like, okay, just maybe even kernel, maybe it's even larger, right? So you will not be able to copy the kernel in memory with those limited registers, right? Okay, and for that, to enable what is called protected mode or 32-bit mode of execution, we say, okay, we will specify a global descriptor table, right? So, and again, that's the beauty of teaching it, that now you understand how it works and what we needed, right? So x86 provides a specific instruction, load global descriptor table, and this is kind of like a struct, and we talked a little bit about, it's a pointer to a struct with a specific layout, which CPU defines, right? So the struct itself will have these 3 entries. So the very first entry in the global descriptor table is not used by convention, so we'll leave it at 0. And the 2 other entries will specify the entry for the code and for the data with a base of 0 and a limit of 4 gigabytes, right? We just say, okay, all memory will be accessible. So almost like no segmentation whatsoever, right? It's kind of transparent to us, right? And the way we define, again, here I'm trying to remind you how it works, that segmentation is always on in front of a paging, right? But the way we define this global descriptor table in assembly is following, right? So we say, look, we'll define a symbol, GDT, right? It's kind of like an array with specific entries, and we will be using assembly macros, right? So to say this one expands to 0, and these macros will help us to define a specific layout of an entry in this table with specific flags, right? So this is executable, read-only, base 0, limit 4 gigabytes. And here, this is for the code, right? And this is for the data. So writable, because you want to be able to write your data section. Again, base 0, limit of 4 gigabytes, right? And then the data structure, which we pass to this load GDT instruction, is the size of this table, because this table can be of variable size. We only define 3 entries, but you can define more, right? And so essentially we say, look, this is the size. We just do the math to compute it, -1. And this is the pointer to the GDT. So it's an address at which this symbol will be linked in a final executable, right? Okay, so this, just again, why am I explaining it? Because you have to start reading the source code, right? The idea is that you will be able to understand what is written, and it's written like that. So if you've never seen it before, it's a little bit unusual, right? So like, it can be intimidating. So, but if someone tells you what it means at a high level, then it's much easier, right? But most kernels are written in a similar way. So if you see another kernel in your life, you will get an idea. Okay, I get it. That's probably a global descriptor table. Maybe it's written slightly differently, but in a way it's the same, right? Okay, so another instruction on assembly in Intel x86 assembly is a long jump. A long jump allows you to essentially specify the code segment, right? And this number will be just, since remember we have entry 0, entry 1, and entry 2. This was for data, this was for code, and this was unused. Our code will have 1, but we shifted by 3 because the first 3 bits are some flags, and I will explain it in a second. So they say, okay, please use this 1 shifted by 3. I'm sorry, I forgot to. Oh, that's interesting. Do not disturb ozone, actually. Okay, sorry. And essentially we say, look, it's at this point, your CS register will get a value of 1 shifted by 3, which is 8, right? And we're jumping to a label which we call start32, right? Okay, let's just take a look at what is the CS format specifically. So this, the first 3 bits are something what we'll talk about. This defines the current privilege level, essentially ring from 0 to 3, right? And in code, there's 4 rings, we need 2 bits. And this is a flag which chooses between global descriptor table and a local descriptor table. And I only explain how global descriptor table works, right? So because we don't use LDT local descriptor tables, right? So we say, since we say we want to have 0 here, so our shift works just finally nice, right? So we say, look, this is 0, this is 0, this is 0, right? So privilege level is 0. We use global descriptor table, and this is our 1 here, right? Agree? Okay, cool. A little bit of low-level details again. Not as important, but my goal is to teach you to make sure that if you read the source code, you can understand what's going on. Source code can be a little bit hairy, right? But again, if you get on a kernel team, you will have to read it. Okay, so we do this long jump, and we jump to this label start32, right? So at this point, again, since we shifted 1 by 3, the CS is 8. Stack segment is still 0. GDT is at some specific address, but inside this 512 blocks, right? I ran it once, and this is the address which I got on my machine, right? And my EAP is somewhere here, also within this pink region, right? So this is all what we know about this machine. So it is this 512 bytes, nothing else. Okay, so you can also instruct the assembly to say generate 16-bit or 32-bit code with this code directive. And since we say, okay, this will be running in 32-bit mode, why not to generate 32-bit instructions, right? So assembly, you tell the assembly from now on, generate 32-bit code. And this is the label where we jumped, right? So since we want to access memory, segmentation is on at this point. The DS segment and SS segments have to be valid, right? So this is what we do. We say segment data. This is entry number 2. Again, shift by 3, load it inside AX register, and essentially move this into DS, ES, SS segments, right? And just these 2 segments we're not going to be using. And we say, like, please move the unused entry into AX and load these segments with 0s, just to make sure that if we do something odd, we'll crash immediately versus like start running in some undefined state, right? So at this point, we say, okay, like everything is ready to run 32-bit code, right? So we switch to protected mode, right? here I show you that now instead of just physical memory, sorry, let me erase everything. Instead of this gray physical memory, we also have a linear address space, right? It provides an identical mapping. We're not going to shift anything. So a zero address in this linear address space, maybe I should actually change it and say logical, right? It depends. Okay, so the segmentation translates from logical to linear, right? So, but essentially what I mean to say that linear addresses are valid. So you say address 0 is mapped to physical 0, right? You might have less physical memory. We might have only 512 megabytes of physical memory. Maybe we're booting on a prehistoric machine, which is tiny, right? We say that we can access everything up to 4 gigabytes. That's a little bit optimistic, right? So we don't really know. So if someone issues an address and like a load instruction which falls beyond the region of available physical memory, you will get an exception, right? The machine will tell you, okay, there is no memory there. So, and at this point we'll crash because we disabled interrupts, but this will be a synchronous exception. So like at this point, it will be a double fold. I mean, first exception, we cannot process this correctly. The system cannot process this correctly. It issues a double fold, and then it will be essentially a triple fold, which will trigger reboot of a machine, right? So if you suddenly will do something like that, your machine will be rebooting in an infinite cycle, right? Just a game. You will see it probably during the homework, right? But nevertheless, we were lucky, so we'll try to just access memory over here, nothing else. And so we have two segments, one for code, this light yellow, and this darkish yellow for data, right? But they are identical. They start from 0, go to 4 gigabytes, right? Okay, so we're running. We say, okay, since programming in assembly is fun, right? But not as much fun as if you want to write a for loop, right? And whoever took the computer organization class, where like people like I and other instructors assign homeworks in MIPS assembly, they know the pain. Like it's doable, it's a lot of fun, but you know, like it's very easy to make a mistake. And this is the reason why actually those people in like Kernighan and Ritchie, right? They developed a language like C. C is essentially a higher level assembly. So it's the language is very close to assembly, but it's still powerful enough to guard you against most of the errors in assembly, right? So there is a type system. You can define data structures, functions, everything like there is a compiler, which will stop you sometimes from using integers as pointers, but not always, right? And so we say, look, like we're done. We really have to do in assembly only the parts which we cannot do in C, because like in C, there is no way to say load something in a CS register, right? Because the language is platform agnostic. It can run on ARM, can run on MIPS, right? So those instructions are not there. So typically C provides like inline assembly, and you can embed some assembly within the C, and it's also a way to program it. But we did it in assembly just for whatever reason. But essentially we say, okay, we want to be done with assembly as soon as possible because it's so hard. We are like one way from like making a mistake by like, you know, like screwing up some of these instructions, right? So let's jump to C as soon as possible. But as I said, right, in order to do this call instruction, we need to have a stack, right? Because this is the first instruction. Remember, it will push the return address or the address which is right here, the next instruction after this boot main, on the stack. And that's why we say, look, we really have to figure out some memory for the stack, right? If I ask you a question, where will we get the memory for this stack? What do you think we should do?
Use the cache.
You can use the cache. Okay, hold on. Caches are not abstraction of addressing or address spaces. It's just a physical abstraction which sits underneath. And you say, I want to address 0. And if it's in a cache, the cache gives it within 2 cycles. If it's not in a cache, you will spend 200 cycles going to memory. But it's still the same address 0. So you can, yeah, so what I'm asking, it works transparently for you, right? So this is, again, parts of the computer organization. So the cache lines that are moved by this But the CPU hardware, they are prefetched from memory and cached and then evicted, right? But any address can be in a cache or may not be in a cache. There is no guarantee. CPU doesn't provide this guarantee. So, but we need to pick an address, right? Address which is valid. So where will it be?
Can you just make the address for this current construction?
That's a reasonable strategy. But what if you like have a loop and you will jump back? Yeah. So probably let's not touch this 512. So it's something what we already compiled. But maybe let's pick some other memory. I mean, clear, there is no malloc, right? So we didn't build any malloc. We just have to pick an address. This is the whole address space, and we are free to pick any address from 0 to 4 gigabytes. Clearly, let's not pick anything here, right? Because there is no memory here. But anything roughly here will be okay, right? But ideally, let's pick something what we're not going to use in the future, because then we will have to move this stack, right? And the suggestion, which, I mean, a reasonable suggestion, is to pick the memory which is not below the current instruction, but below this 512 bytes, right? And so exactly this address 7C00, if we say this is the top of the stack, this is where our ESP will be pointing, it will grow downwards, because this is how x86 grows the stack. So if you start pushing in the stack, ESP will be decremented, right? So why not to pick this address, right? Because we, like, ideally what we do, we have to read the hardware manual and say, maybe BIOS has something magical, or like, if you write into this addresses, you will trigger a disk transaction, right? It can happen, so you have to be careful. But thank God, like x86 is designed in such a manner that those addresses are not used. Like this gap is okay, right? And we say, okay, like this is why we essentially say we use the start. Remember, start is a label which was compiled to be 7C00, right, in X. So we use it as a number because we know that this is an address, right, and load it into the ESP register. This is where the ESP register will be pointing. Agree? Okay, so we figured out the stack, so we can invoke this very first C function, boot main. And the boot main is the function which will read the kernel from disk in memory, right? So again, I'm showing you the source file here. So it's still part of the bootloader. I show it here so you don't get confused. It's not yet the kernel. It's the bootloader, which is compiled separately from the kernel. But again, we're reading the kernel from disk. So it's kind of a familiar job because it's exactly what you just did in the homework, right? So you'll say, okay, yeah, I will figure out where, like, I will figure out the L file from disk and we'll load it somewhere. And again, you have a little bit of a problem here. So you say, I need to pick an address in the address space where I want this kernel to be loaded right now. So again, so how we will pick this address?
We could either move up right after our block, or we can pick somewhere in the list.
You're right, but this is where we have to be careful. It turns out that this memory is used for magical purposes by the BIOS. And remember my demo when I was doing Hello World. So remember that move instruction into memory somewhere over here, and we didn't pay attention which memory I was using, right? But apparently it's a frame buffer. Meaning that if I write some H here in a key, right, then it will get picked up by the display hardware and will be placed on a screen, right? So at this point, we have to read the manual and say, okay, like just figure out what regions are available, what are not available. And it turns out that regions above the first megabyte are available and not used by the BIOS. Again, it's just like, it's a specification of a personal computer, PC, right? And they say, okay, this is how we want our address space to look like, so everyone can develop software on top of it, right? And they say, okay, everything above the first megabyte is available to you, right? And we say, look, lucky. So we say, we're so smart, so we will put this 10000 is exactly 1 megabyte. Let's double check, because who knows, maybe we're wrong. I'll use Python again and type it in, x0 000. No, wrong. This is 64 kilobytes, so we need another 0, right? Maybe I was wrong. Maybe it's not 1 megabyte. Yeah, I was wrong. So apparently BIOS is more permissive. In my latest kernel, which I was building, I was picking first megabyte. But apparently this is just good enough, and it's we are good to go. Anything above 64 kilobytes is not used, right? Sure. So let's load our kernel there. Why not? So we say, well, just to make up this address in C, you say, I will take this number and I will convert it, typecast it to a pointer. And this elf pointer, actually this elf pointer, the address 64 kilobyte. And maybe I was a little bit wrong, but we use this as a scratch space. So maybe I will load the kernel at a slightly different address. Maybe I was wrong and we will load it at first megabyte. Maybe I forgot, right? But you say, look, this is the elf header. So you're doing what you were doing in a homework. You say, I'm expecting to read the elf file from disk. At this point, you have to make an agreement that the kernel, you know where the kernel is located on disk. And the agreement here is that it will be located at address at address 0, although I was saying that the bootloader should be located there. So let me clarify it. But okay, maybe let me take it offline and figure out why we're using 0 here, right? But the idea is that, okay, if we have a function which says, okay, read this segment of disk into a memory location pointed by the elf pointer, and you say the size, you're reading the first 4 kilobytes of that elf file, which is sitting on disk. Why for just one page? Just because you know that the elf header fits there, and most likely you're optimistic here. So really, you need to like first read the elf header and then read the program headers, and let's see what we are doing here, right? So, but anyway, so you say I have a function which read disks, which can read a disk. The question is, okay, function. And I was telling you that to read a disk, let's just go here. To read a disk is to, you say the interface is provided with this collection of something what is called ports, right? So x86 says that there is a magical space of ports starting from 0 going to 64 kilobytes, right? It's individual ports. So port 0, port 1, and so on, right? To the power 16, right? And you use the assembly instructions which are out port and in port. So out and in, right? And here we wrap them into a C like interface because we don't want to use assembly, but essentially this function out B outputs 1 byte into a port with this number. And you say, look, if I have a hard drive, the convention is that the system will, if you write something into this port, it will reach the hard drive, right? And what you doing here, so let's take a look at this specific command. We say wait disk. So our goal is to read a sector, but we say let's first execute this wait disk because we know what the protocol is between the with the disk, and we say like we have to make sure that it's ready. And what we're doing here, we're reading this port 1F7, right? And we're reading some specific bits of this port, and we're looping until we see a specific value, which according to the protocol tells you that the disk is ready to go, ready to take a next command, right? So essentially it's an infinite loop, and you might get unlucky. Maybe a disk is not connected, so you will get stuck here forever. But in a good case, you know, your disk will reply with this value 40 in this port, and you say like the hardware is ready, right? So essentially when you're in something from a port, it really traverses all these buses, which I was, this is your hard drive, and essentially just reaches the CPU, and this value, this byte, which you're trying to read right through those buses, will be available to you at this specific port with an in instruction, right? That's an interface with hardware. That's one of the interfaces, and we will take a look at others later, but that's not bad, right? So you say, look, we wait for the disk to be ready, and then you say, this is the protocol, roughly speaking, to the disk. You say, I want to read one segment, so count is 1, at a specific offset in the disk, right? And what is, there is probably some mathematics here which happens to that the offset has to be split between multiple ports because each port just takes a byte, right? And what you're saying is that that's essentially you're just essentially splitting the 32-bit value of an offset into like byte chunks, right? And at this point you say, please read the number of sectors. So sector is 512. We said we want to read 496 bytes, right? So it's 512 multiplied by 8, right? So x20 should be 8 theoretically, right? But let's double check. Maybe I'm wrong again. So it's 32. Why is it 32? Okay, 512 by 32. Let's see the number. Maybe sector is a different size. 512 by 32. So apparently we're reading 16 kilobytes. Okay, maybe. Why is that? So maybe I'm wrong, and command is actually okay. Again, maybe I'm wrong here a little bit, and I will clarify it for you. But just to make sure that we read a specific number of bytes from disk, right? And again, we say we'll read for the disk to get ready, right? And and issue this specific command which will allow you to long. So sector sec size. So okay, let me come back to this, like to make sure that we understand it in details. And we will come back to this maybe towards the end of the class when we'll start looking at device drivers, right? But trust me that we read something from disk here, right? And what we're doing here is, let's just come back here. Okay, not here. We effectively read 496 bytes into this location in memory where we have the ELF header. So what we first thing we do is we check if the ELF magic really matches, right? I haven't seen you doing this in the homework. We just blindly assume that we read the ELF file, but here we're a little bit more careful. We say, okay, like really, did we read the ELF header? Well, likely yes. If not, we return to boot ASM, and then we will handle the error. Essentially, we fail booting. But if we really read the ELF magic, we say, okay, we know that it's an ELF file, so let's keep reading the ELF headers, right? So what we do here is essentially you say, we just optimistically assume that ELF headers fit into this first 496 bytes, and we say this is the header itself, ELF, and the program headers are somewhere over here, right? And we say we just typecast, saying this is an offset. So literally, if the offset within a file was some number, then the ELF plus offset will give us a program header array in memory, right? And we implement a familiar loop, essentially saying, okay, we'll keep looping, reading the headers one by one. And essentially what we will be doing here, since we know that this is a physical address at which it has to be loaded, we say, please read here. We just assume that this physical memory is available, and we link the kernel correctly. So we will be reading this essentially from disk one by one, right? And here, for each of this, what is this line? What we're doing here, if program header mem size is larger than the file size, Do you know what happens? I kind of know, I guessed. Do you know what we're doing here? No. Good exam question. I can guess in 2 seconds, so you have to guess in like 5 minutes on the exam. I believe what happens here is that you say, look, there are some sections like BSS, right, which are not on file, so we don't keep them. It's a little bit of an ugly code here, so you have to be a little bit more explicit, saying that if the section is BSS, then just fill it with zeros. But here you just do a simple check. You say if the memory size of this program header is larger than the file size, so please fill this memory with just zeros, right? I think that this function stores bytes is essentially says, okay, this chunk, which is a chunk beyond the file, just fill in the memory, initialize it with zeros, right? A little ugly, but again, you have to try to guess what the code is doing, even if it's written by a different person, and even if it's not completely clear, right? But nevertheless, so we read everything like we read the ELF file from disk to memory, right? Most of this were like some sections, and the last fraction we're a little bit confident here. So in a general case, it will not work. But what I'm telling you is that the kernel is compiled in such a manner, and we control the compilation environment, that we put the BSS at the very last, just to do this trick. BSS can be somewhere in the middle, but we will use a linker script to say like BSS will be at the end, and that's why it works, right? And we do this trick. Okay, so the kernel is in memory. I was telling you that we were going to load the kernel at the first megabyte. And nowhere around here this address showed up, right? Because the only address which we were using was this scratch address, this one. It's 64 kilobytes. But I was kind of claiming that the kernel goes into this first megabyte. How did we control this address? Yeah. It's in the L header, exactly. So because we blindly followed this thing, we say, okay, whatever this address contains, and in order to achieve what we want, we have to configure this address to be 1 megabyte. And I'll show you later how we do it, right? But okay, just trust me. So we loaded it at the first megabyte. Now we want to start executing the kernel again. So what we're doing here, we say, wow, entry function. We know that, again, it's not a convention. We just generated the code in such a manner that entry is a void function, right? So you say elf entry, and we're very careful to make sure that this is somewhere here in the first megabyte, right? Will be our function, and we call the entry point of the kernel, right? A little bit of a hackery. Just you can make it cleaner, but you can do it. Okay, let me stop here for a second. So any questions? So we are jumping into, when we go into the entry, we will leave the bootloader, and we'll start running the kernel. Any questions?
If we were to ask a question on the exam to like parse the line on SOSB, would we give it more information on the exam, like that red sauce and instruction or something like that?
Exam will be open book. So essentially, and open everything besides searching on the internet, because search on the internet just yields unpredictable results, and asking for help online, essentially like chatting with your friends, right? So what you're gonna do is that, and this is what you should do, right? Let me show you a couple of ways to do it. So you say x86 book should be your body. Okay, this is not the book. That's actually the book, but we need not the books. We need the source code. Man, really? Okay, let's edit the link. In revision 10, that's a book. We don't need the book. No? Okay, let's go to our wonderful 5460 website. That's, say, x86. So where's the source code? Towards the end, we say book and a printout of its source code, right? Okay, let's go to this printout of a source code. This is a PDF, and you say, look, I clearly don't know what STOSB is doing. It's defined at line 0492. So you search 04 92. And you quickly look it up. So you say, wow, inline function, which does stores B, right? And this weird inline assembly syntax. So it doesn't help you like a ton, but you like the next step is stores B. What is stores B doing, right? So you say, look, store string. So essentially, stores a value from the EAX register into the destination operand, which is a memory location, right? So let's at this point you say, look, I'm almost there. So it's ideal to understand the syntax as well. So you say there is this also rep prefix, which is hard to explain, but rep allows you to execute this instruction multiple times, right? So that's why there is a counter, right? Okay, so not clear what stores B is doing. Stores B example. Search on the internet at this point. So essentially here, like you have to use a little bit of knowledge to guess that you can execute this instruction multiple times with this rep prefix. So it's kind of like mem CPI or mem set. So that's what you have to do. Alternatively, you say, look, I don't want to deal with a book. So instead you say, I'll just quickly go to the x86 source code and I use vim, and I will use the grep command, which we were using before, and I say, look, search in all these files, and it will immediately land me on this all the like instances of a stores B, and this is the definition, right? So it might be a little bit faster for you. If you use your favorite Visual Studio, it might come with cross-referencing, maybe even GitHub cross-references x86 these days because it just cross-references C, right? Okay, good. Any other questions? Yeah, so we probably, on the exam, it's unlikely that I will be asking low-level questions about assembly because I understand that, okay, no one is required to know what the rep prefix is and stuff like that, but I might ask questions about what this loop is doing, right? And you have to understand like the logic of this loop at a high level, right? So I got confused about why is that we're loading the sector 0, and I think the answer, I can quickly try to verify it for myself as well. Just let me quickly switch here. So if we go to the make file and you say QEMU, the way we start QEMU, so here's the command which creates the disk for the x86 system, right? So what we do here, and this is for the in-memory disk, but this is a real one. So the boot block comes. So dd is a disk copy command, which says essentially initialize it first with all zeros in line 87. Line 88 says, okay, please move the boot block at the very beginning of the disk. This is what the BIOS expects, right? The sector 0. And move the kernel at the sector 1, right? So it literally sits at sector 1. So then we are confused and we say read seg. We say like, why is it we're reading, it looks like we're reading the segment 0 instead of 1 right here. And I don't have a good answer, to be honest. So we should figure it out. So offset, what are we doing here? Okay. Ah, man. Okay, I skipped this function, so I apologize. So in my source code, I probably wanted to simplify the exposition here, but essentially, what we say here is that no matter what we do, we will add this one, right? So essentially, this is a function which says if you try to read the offset 0 from a kernel, from a disk, it's kind of like the idea that you have a boot block and a partition of a disk, which is in some way, is something outside of the boot block, right? So that's why you add one here, and then you use this function to do the read section, right? And the section size is defined somewhere over here, so 512. We can probably figure out the mass. Why is that? This is the function which we looked at, read sector versus read segment, right? So, okay, lost a little. I'm lost too, but don't worry. So, but this is how you have to go about it. So if something is not clear, just try to understand what's going on in the kernel source code. And here it gives you a comment that it translates bytes to sectors. Essentially, kernel starts at sector 1, right? So because 0 is taken by the boot block. Okay, let's keep going back to this one. So we jumped into the entry point in the kernel. That's our goal, right? We did it. So again, the kernel itself, remember the plan. We want to enable page tables. To enable page tables, we have to talk a little bit of assembly and before C. That's why we again landed ourselves in assembly. So the kernel starts again with first assembly instructions, right? So this is the entry label inside the kernel. And what it does at the very first thing is it will try to enable the page table. And for simplicity, we're going to use the 4 megabyte pages. Remember, x86 supports 2 page sizes, either 4 kilobyte pages or 4 megabyte pages. And we say, look, we're going to enable 4 megabyte extensions. For that, we read the control register 4 into the register, set a specific flag which enable this extension in the register, and then write the register back into the control register 4, right? So you cannot set a bit directly on the control register. You need to first read it into like a general register, set a bit. This OR does not work on CR4, right? But that's okay. So you say, look, we're going to be using a 4 megabyte pages. This is my kernel sitting at the very first megabyte. So this is the address. So remember, I was struggling to figure out this 0 because this would be like 64 kilobyte. But now I'm saying, okay, this is first megabyte, right? And the way we achieved it is through. Let me quickly show you here. We achieved it by LD. Okay, let's take a look at the make file again. And if we say kernel, let's remember that I was telling you that the linker can take a specific script as an argument. This is the script, kernel LD. And if we look at it, kernel LD, we say, by the way, this is how we want the kernel to be compiled. So we say, well, use this address, right? And this is the first megabyte, and as a physical address, right? So, and then remember I was saying that BSS should be at the very end, and this is how we control that. So we essentially said, okay, BSS will be here, just because we want to do this ugly trick, which we've seen, where we set the bytes outside of the file as a BSS. Oh, sorry, that will never run again. Let me close everything. Okay, so this is where our kernel is sitting, this yellow part. Remember, I'm using yellow for the kernel always. So that's why it's yellow here. So it's still physical address, like still only segmentation is enabled. So it's linear addresses, right? Which translate from linear to physical without any shifts, right? Okay, so our goal is to enable the very first page table, right? So again, my reminder, we're going to be using 4 megabyte pages. This is how the translation works. We all know it. And what we're doing here is we will be using this symbol. And this is a C definition of an entry page directory. We're going to move it into the EAX register, right? And then we're going to move EAX into CR3. Remember, I was telling you that CR3, control register 3, is a machine register which keeps a pointer to the root of a page table, right? So if I ask you, like, what should be inside, how will we define this page table? So clearly, it's just like you say, remember I was telling you, if we, CR3 is a physical address of a page table, and this is a macro which translates from virtual addresses to physical addresses, right? And extends it with zeros, I guess, at the very bottom, right? But essentially, you say whatever my C code generated here, this is where the page table will live, right? So if I ask you how to define a page table in C, what will be the guess? A struct, yeah. A struct with how many entries? 1024 entries, right? It's a little bit ugly way to define a struct. How do we define structs which have many identical entries? Arrays, right, exactly. So let's use an array or array of structs if we want, right? Because that will be better. So each entry will be a struct, and it will be an array of structs. Okay, let me take a tiny detour here. So the end goal for the virtual address space for us is to have this 2 GB and 2 GB split. So essentially, only the lower half of the address space will be accessible to processes. And the higher 2 GB will be kernel memory. So this is how we want it to be in the end. Right now, our kernel sits somewhere over here, right? So if we just enable one-to-one mapping, the kernel will be found at address first megabyte, right? And it's okay for the purposes of booting right now. So this is 1 megabyte. But what we want to do is just to make sure that the kernel will be mapped here at the 2nd gigabyte, an address which looks like this in hex, right? So it's all 8s, 8 and all 0s, right? Okay, let's take a look here. So this is where our kernel is sitting, first megabyte, right? This is somewhere where the entry point is in physical memory. So it's right here, right? So this is where we're currently running. This is our instruction pointer, right? Our stack is still sitting here because we didn't change the stack yet. Okay, we say we'll define 2 entries in this page table. One entry, entry 0, it will map virtual addresses from 0 to 4 megabytes to physical addresses, or this is defined here, to physical addresses from 0 to 4 megabytes, right? And the second entry, entry 512 in this array, will map virtual addresses starting as the 2nd gigabyte to 2nd gigabyte, sorry, 2nd gigabyte plus 4 megabyte to the physical addresses from 0 to 4 megabytes. Just 2 entries. It's a little bit magical. Why do we only care about 2 entries right now? I will explain it in a second. But essentially what we're trying to achieve is the mapping which allows us to eventually move the kernel from the lower addresses to the higher addresses. And I will explain it in a second. So, okay, so we have to be a little bit careful with this array. First of all, remember that like our macros will zero out the lowest 12 bits, right? Because we say like the page table, the root better be aligned. And so we use this aligned attribute in C to say aligned to the page size. So this is the 496 bytes, right? So exactly all lowest 12 bits will be zeros, right? And you say it's an array of entry page directory of NP entries, which is, we can guess 1024, and entry number 0 will create it. So we say, remember, we want to map physical address 0 to a virtual address 0 with some permission flags, right? So page table present, page table writable, and page table PS stands for what? For do you okay, don't know what PS stands for, right? But we will figure it out in a second. And the second entry is 512, and this is essentially how you compute it with this. So you can say, okay, I just do this math, it comes out to 512, and again, it will be mapped to physical address 0, PT present, PT writable, and PT PS. So let's quickly, since we don't understand what these flags, we don't fully understand what these flags mean, let's do this trick again. So we can either go online, let's go just quickly online and check the x86 printout to see what the what this flag is. PT PS apparently defines a page size, right? So look, it's again like, look, I didn't remember from previous years, right? So P stands for present, writable stands for writable, W stands for writable, user stands for user, and PS stands for page size. Meaning that's a bit in a page table entry which says that the next level is not present, meaning it's instead of a 4 kilobyte page, it's a 4 megabyte page. And x86 allows you to mix entries. Essentially, you say, look, I enable those extensions, and the hardware will take a look at the root of the page table, and depending on whether this page size bit is set or not, will either go to the next level and try to translate a 4 kilobyte page, or we'll stop here and say that the next translation is done because the page is 4 megabytes, right? Which means that it's at your discretion to essentially create a page table in which some entries will leave to the second level and then to a physical page, and some entries will immediately leave to a 4 megabyte physical page, right? You can mix them. Essentially, you say part of my address space will be 4 kilobyte pages, and part of it will be 4 megabyte pages, right? Agree? Okay, good. A little bit of like low-level trivia, but still, okay, we quickly figure out what it is. And remember, remember how translation works. That's why we put 0 and 512 here, because 0 will translate virtual address 0, right? And 512 will be translating a 512 chunks of the address space. So if it's 4 megabytes multiplied by 512, you will exactly land on 2 gigabytes, right? Because the entire address space is 1024 chunks, right? Okay, so in P entries is 1024, that's correct. And so essentially, we are creating the address space which maps the kernel twice, right? So the kernel sits at address 1 megabyte, and the kernel set sits at address 4 megabytes, right? So it's, let's put it this way, 2 gigabytes, and this mark is exactly 2 gigabytes plus 1 megabyte, right? But in physical memory, this is just one kernel, right? So these two things, they come to the single set of physical pages. We double map the kernel, right? I'll explain in a second why we did it, right? Because our EAP is still here. So our EAP is somewhere over here, right next to the start label in the first megabyte of the addresses, right? Okay, so that's our future virtual address space defined by the page table. So the page table itself sits somewhere within the kernel. Since we defined it as an array, it's in the global section, in the data section. Agreed? Okay. It has only 2 entries, as I was saying. One mapping 0 to 4 megabytes, and one mapping 2 gigabytes to 2 gigabytes plus 4 megabytes. Okay. We will turn on paging now. It's controlled by control register 0. Again, you read the manual for these flags, but okay, just if someone tells you how to do it, you already know, right? So CR0 into the register EAX, enable 2 flags, right? And move them on the EAX register and load the EAX with CR0, back into CR0, right? Specifically, I believe that this instruction immediately kicks in paging. The very next instruction after this one will be executed with paging enabled, right? So let's double check very quick. So we will, up here, we will read entry.s, right? This is where we were running. And we say, turn on paging, right? let me ask you a question. So at this point, right after this instruction enables paging. So this instruction the very next instruction will be translated through the page table, right? What's the instruction pointer? Where does it point at this moment? Let me erase everything on this screen. My instruction pointer is still somewhere here, right? Which means that the very next instruction has to be translated from somewhere around here, right? Because we didn't change the instruction pointer. We just executed a move instruction, and it magically enabled paging, right? Nevertheless, our goal is to place the kernel in the upper 2 GB. In the end, we're gonna jump here, and we'll start executing actually here, right? But in this very short transition window, we're still running with paging on, but the instruction pointer, EAP register, is still pointing here. So if we don't have this entry in a page table, we'll immediately crash with a page fault, right? That's why we double mount the kernel for this tiny transition period when we say, okay, we're still running here, but our goal is to start running here. The moment we jump here in the higher addresses, we can disable this entry, essentially say, okay, forget about it. We no longer need it, right? But that's essentially the reason why we double map the kernel, right? To do this trick so you don't crash. And just to make sure that we are not confused about it, there is a little bit of magic here. The kernel itself, if you look at this linker script, which we were using before, if you're very, very careful, the kernel is compiled and linked to run at address 801040, right? It's an address which is 2 GB plus 1 MB. So all global addresses all global variables in the kernel will be linked to be in that location, right? So above the 2nd gigabyte. However, we still managed to run the kernel at the lowest addresses. So what was the magic? How we did it? Because like every symbol, so essentially if you do something like read alf of a kernel. Oh no, I have to compile it real quick. Let me compile. Really? Good enough. And we say, show me the symbols, essentially -s, right? So I say, show me all the symbols in the kernel, and type to. If you say something like, okay, main. So function main is linked to be at this address, 2nd gigabyte, right? For example, the name entry page dir. Really? Let's do it again. Entry page directory is also located at about the 2nd gigabyte, right? So the linker followed the instruction. So linker really is compiled and linked the program, as I was explaining. All the global variables are about the 2nd gigabyte, but we still were able to access them. So what was the magic? The magic was the following. We were very, very careful, and every time we were accessing a symbol from which we knew exists in the kernel, we were using this macro, which translates virtual to physical. As you can guess, this macro just subtracts the 2 gigabytes. So essentially, when you say like this entry page dir, the number will be 8010 and whatever some bytes, right? So it's about the 2nd gigabyte, but the macro will subtract the 2 gigabytes and will essentially that will be matching physical address, right? So before we enable the page table, we were doing this translation. So every time we were trying to access something with the kernel, in the assembly, since we control what we're doing, we can do this trick. Is that clear? It's a little unusual. Again, the reason, I mean, I can skip over this. I can say just like, forget about it, let's just start running in main. But then again, we have a little bit of time, and people who will watch these lectures again, or will really be digging the source code, will ask this question sooner or later, because you say, okay, what is going on? If you sit here with a GDB and I ask you, what is this? How does it work? The symbol is clearly like a different number. That's what's going on. And let's quickly just verify our understanding. So we say V2PWO, and just quickly grab. Same for the start, like we cheated here. We said, okay, the entry, which is located in the second gigabyte, the assembly file, like just tell the assembly that the entry starts in the first megabyte, right? So that's a little bit of trickery again. But this is your, this is your definition of the macro. Let me just stop here. So essentially you say X minus kern base. So we don't zero anything, right? So we just say, so since kern base is 2 gigabytes. It's defined right here above, right? So that's how we get away with this. Like all the symbols are in the upper part of the address space, but we still can use them from assembly. Okay, so booting turns out a little bit more involved than just simply jumping, right? But I just wanted to explain how it works. Okay, so we have this page table which double max the kernel. We say our main goal is to quickly forget about the first megabyte and keep running in the second gigabyte, right? Question?
How do you run macros in assembly?
It's assembly. No assembly supports macros as well. It's just powerful enough to do that. It's not. I'm not sure that it's the same syntax as C macros, but they exist there. And I don't know if LLVM does. I'm pretty sure it does, but maybe with a different syntax, but I'm not sure. I'm pretty sure it does, though. Just because people realized very quickly that, okay, it's so cumbersome to go without macros that we just implement them. Okay, our goal is to forget about it, right? Again, and our goal is to run C. The moment we forget about this first megabyte, it means that our first stack, which we allocated in this 7C00 and down, will disappear, right? So we have to switch to a different stack. At this point, we say, okay, this will be our permanent kernel stack. And we say, like, where will we define it? What would be your idea? We say, like, it will be in a kernel data section. Why not? Just one stack, 4096 bytes, defined like this, with this COM instruction, which essentially says, okay, this is the number of bytes, right? Okay, cool. And that's what we're doing. We say, we want to forget about the lowest part of the address space. So please use our new stack. And remember that now this is a X8010 something here address. Again, if I do read alpha, we'll see this address, right? I recommend you doing this. And since we want to go to the very top of this stack, we add the stack size, right? Because this is just an array, and we say we're going to go with the end of the array. We load it into the ESP register. And at this point, what will be the next instruction? Who can guess? Call? Yeah, call. Call what? Huh?
I'm not sure.
Main. I mean, we're close. We're almost done. The time is running up, right? So we say, okay, so this is the data section. This will be our new stack. It will be double mapped, right? And at this point, we can say we try to call main, but assembly doesn't understand this trickery which we involved underneath, right? That we want to move to a different address range. If we just do call main, remember, it will just generate a relative address. Like it will be like, I don't know, like 355 bytes forward or backward, right? But we really want to go to 0x8010 something here, right? That's why we're doing this. So we say, okay, we don't want to deal with assembly, which will, if we put in call main instruction, it will don't understand what we're trying to do. What we're doing instead, we really load this number into the EAX register and then just jump to it, right? That just to prevent this relative jump from happening. But essentially what we're doing, we're jumping in main. And at this point, you find yourself here on a new stack The stack is empty because nothing was running before us, or something what was running, we'll happily forget about it, right? But that's your main function. So, and we essentially will go forward, understanding how the kernel initializes itself, essentially setting up a physical memory allocator, setting out the new page table, which will be a fine-grained 4 KB page tables. This entry page directory, we use it only during the boot, and it just just to simplify the boot sequence, and so on. We will just detect other CPUs, and we'll go on forward from there. But today we ended in main, right? So that's, again, x86 main function here. We're now currently running inside the kernel. We'll never come back to the boot again, so we'll continue in main, obviously. And okay, so you'll learn how the kernel is continuous initializing itself, and this just starts. The goal at the very end of the main, our goal is to start something what is called an init process, right? Essentially start running init, and init will start shell, and shell will put us a command prompt. So essentially, if I do something, and I'm not sure that my build environment is correct, but if I close everything here and do make QEMU without what is it? I was doing something weird, and maybe my build environment is off, and I don't know how to resolve it. Oh no, make. So what we will see soon, this is my boot of the kernel, and this is I'm inside x86 now. So that's what we start doing soon. So essentially, that's my first shell inside x86 running under QEMU. Okay, so I'm done for today. So any questions? We're all good? Boot is a little bit involved. So your homework will ask you to boot into main. So, and we'll ask you to set up the first page table. That's why, I was so detailed. I wanted to explain the details of the assembly syntax. You're not gonna have to read anything from disk. The kernel will be loaded in memory by the grub bootloader. I will try to talk a little bit about the homework more, but just get ready then. This is what's coming. Okay, thank you. See you then next week.
Give me the homework and target the policy.
Not